Hello and welcome to our video on the product rule, quotient rule, and higher order derivatives. The objective for this video is 1, to find the derivative using the product rule. Number 2, find the derivative using the quotient rule. The third one is to find the derivative of trig functions. And the fourth objective is to find higher order derivatives of functions. Let's start out by taking a look at the product rule. The product rule is to find the derivative product of two differentiable functions, f of x and g of x. What we have is, in symbols, the derivative of that function, of the product of f of x and g of x, is going to be f prime of x times g of x plus f of x times g prime of x. Or in words, the derivative of the first times the second plus the first times the derivative of the second. Take some time right now to copy those words and the symbolic product rule down in your notes. Let's take a look at the proof of the product rule. We're going to let f of x, in this case, be a function that's defined by u and v, where u and v happen to be functions of x. Okay? And they are continuous and differentiable. So, f prime of x, by the definition of the derivative that we're familiar with, is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Well, f of x plus delta x is just going to be the product of u plus delta u times v plus delta v minus f of x, which is just uv, all over delta x. And of course, we're taking the limit of this as delta x goes to 0. At this point, what I need to do is multiply out that the u plus delta u and v plus delta v. So when I do that, I will get u times v plus u times delta v plus v times delta u plus delta u times delta v, and then we still have that minus u times v tagging along at the end, and it's all still over delta x. And of course, this is the limit as delta x goes to 0. Now, what happens here is we'll notice the u v's drop out. And so what I'm left with now is the limit as delta x approaches 0 of u delta v plus v delta u plus delta u delta v over delta x. Which when I break this up, and this is a key part, we want to break that up into 3 fractions. So we have the limit as delta x goes to 0 of u times delta v over delta x plus v times delta u over delta x plus delta u delta v over delta x. At this point, you need to keep in mind a couple of things. Number 1, as delta x goes to 0, I also know, because u and v are differentiable functions, as delta x goes to 0, I know that delta u and delta v are also going to 0. Okay. The other thing is, when I take a look at, like in this first one, I have the delta v over delta x. Well, as delta x goes to 0, you should recognize that. It's just basically a slope formula, and that is the change in v over the change in x. And so I know that this, as delta x goes to 0, ends up becoming just the derivative of v. So what happens at this point, our limit that we have here is equal to u times v prime. That's the first piece right here, plus v times u prime plus, now here's the other part. Now the delta u over delta x would be equal to u prime, but it's going to be multiplied by delta v, which we know as delta x goes to 0 is also going to be 0. So this third fraction just becomes 0. And so what I end up having here is that the derivative with respect to x of f of x is equal to, because all this is commutative, I can rewrite it as u prime times v plus u v prime Or, as our words say, the derivative of the first times the second plus the first times the derivative of the second. Now let's take a look at a couple of examples. Right now, let's take a look at this example that we have. F of x equals x squared cosine x times cosine x. And we want to find the derivative. So I know the derivative of this function with respect to x is going to be by the product rule. Remember the chant. It's the derivative of the first times the second plus the first times the derivative of the second. The derivative of my first, in this case, the first is x squared, so its derivative is 2x times the second, so times cosine of x, plus the first, which in this case is x squared, times the derivative of the second. And we know the derivative of cosine is negative sine of x. And so, for this particular problem, I know f prime of x equals 2x cosine x minus x squared sine x. Now let's take a look at a problem for you to do. In this case, we have f of x is equal to the quantity x squared minus 4x times the quantity of 4x cubed minus 2. What I would like you to do is I would like you to pause the video and take the derivative, find the derivative of f, find f prime, using the product rule on this problem. So pause the video, find the derivative, and once you come back, we'll go through and look at what you did. Welcome back. In this case, for this particular problem, you should have come out with the first derivative, f prime of x equal to 20x to the fourth minus 64x cubed minus 4x plus 8. Assuming you went and multiplied everything out and simplified, combining all the like terms. Let's see how we got this. In this case, we know it's a product, so we're going to use the product rule. So I know f prime of x is equal to the derivative of the first, which will be 2x minus 4, times the second, which is 4x cubed minus 2, plus the first, which is x squared minus 4x, times the derivative of the second, which is 12x squared. At this point, I would need to go and multiply everything out. So I'll have to FOIL these first two. And when I do that, I get 2x times 4x cubed gives me 8x to the fourth. 2x times the negative 2 gives me minus 4x. Negative 4 times 4x cubed is negative 16x cubed. And negative 4 times negative 2 is a positive 8. Plus, when I distribute this 12x squared inside, I will get the 12x to the fourth minus 48x cubed. At this point, it's just a matter of combining like terms. 8x to the fourth plus 12x to the fourth does give me the 20x to the fourth. Negative 16x cubed minus 48x cubed gives me the negative 64x cubed. And then we still have the minus 4x and plus 8 at the end. So we get our final derivative of 20x to the fourth minus 64x cubed minus 4x plus 8. Hopefully you got that answer. But if you didn't, I hope you understand now what mistakes you made and so that we can get those corrected. Now let's take a look at the quotient rule. The quotient rule is to help us find the derivative of the quotient of two functions where I take f of x over g of x. And again, f of x and g of x should be differentiable functions. They must be differentiable functions over the interval. So what the quotient rule says is that if I want to find the derivative with respect to x of f of x over g of x, it's going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the square of the denominator, provided that in this case g of x, our denominator, does not equal 0. So derivative again of with respect to x of f of x over g of x is going to be f prime of x times g of x minus f of x times g prime of x all over g of x, that thing squared. Or in words, helpful chant that you can use, it's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So pause the video, take a couple moments, write these things down, and then we will go on and take a look at some examples. Let's take a look at an example. We'll save a proof on this one for another time. In this case, g of x is going to be x squared minus 1 over 3x plus 7. I want to find the derivative of g. So I know g prime of x by the quotient rule is going to be the derivative of the top. Well, the derivative of x squared minus 1 is just going to be 2x times the bottom, which is 3x plus 7, minus the top, so in parentheses, x squared minus 1, times the derivative of the bottom, which in this case is just 3, all over that bottom squared. So it's 3x plus 7, that quantity squared. At this point, we would go and distribute and try to simplify this. I'd have g prime of x equals 6x squared plus 14x minus 3x squared. Now be careful because you got a minus on and there. So it'll be, and then it will be plus 3 all over 3x plus 7, that quantity squared. And when I combine like terms, I will get that this is going to be 3x squared plus 14x plus 3 over the 3x plus 7, that quantity squared. So in this case, I know that g prime of x is 3x squared plus 14x plus 3 over 3x plus 7, that quantity squared. Now we'll have you do one. Okay, what we're going to do on this one is I'm going to have you do a function. Oh, I don't know. I'm just going to kind of make one up. I'm going to say f of x is equal to sine of x over cosine x. So what I would like you to do right now is you take the derivative of sine of x over cosine of x using the quotient rule. And once you get finished, I want you to simplify that as far as you can. And when you come back, we'll go through the solution and see how you did. Welcome back. Hopefully you got your final answer, and I'm hoping that your final answer in this case came out to be secant squared x. If not, let's take a look at how it worked out. In this case right here, when I have the quotient rule, f prime of x is going to be the derivative of the top times the bottom. Well, derivative of sine is cosine times the bottom, which is also cosine, minus the top times the derivative of the bottom. Well, the top is sine x, and the derivative of cosine is negative sine x, and we're going to be over the bottom squared. Now we simplify that. Well, that numerator, cosine times cosine, that's just going to be cosine squared x, minus sine x times negative sine x is just going to be plus sine squared x over cosine of x, that thing squared, is cosine squared x. Now you look at that and you say, wait a second. I'm hoping every one of you looked at that numerator and you said, I know what that's equal to. That's a Pythagorean identity from what we did last year in trig, and we know cosine squared x plus sine squared x, we know that equals 1. So this is just 1 over cosine squared x, which we know is secant squared x. But the really cool thing on this one is if you look back at what we started out with, f of x is sine x over cosine x, you say, wait a second, I know what that is. That's tangent x. So what this does is this proves to us that if I want to take the derivative of the tangent of x, I will get secant squared x. In other words, we now have another derivative formula. Not only do we have the product rule and the quotient rule, but now we know that the derivative of tangent is secant squared. Let's do one more example involving trig functions. I know I am going to let f of x equal secant of x. So in this particular problem, I'm going to go through and I want to find the derivative of secant. Now, there's a lot of different ways we can think of secant. And the way we're going to work with this one is we're going to think of secant as 1 over cosine of x. And we're going to use the quotient rule to help us find that derivative. So, what we have on this one, I know that f prime of x is going to be the derivative of the top times the bottom. Well, the top is a constant, so that's going to be 0 times cosine of x minus the top, 1, times the derivative of the bottom, which is going to be negative sine x, all over that bottom squared. So I'll get cosine squared x. When I simplify that, that is just going to become sine x over cosine squared x. And right now you might be saying, well, wait a second, that really doesn't simplify to anything I remember. And, you know, it doesn't really look like one of the identities we have, but we can go through and move things around a little bit. I know that is equal to, that's the same thing as 1 over cosine of x times sine x over cosine of x. Notice when I multiply the fractions, I multiply them through. I'll get sine x over cosine x, or cosine squared x. And so what I have here, what's on the left is 1 over cosine x is secant x. And what's on the right is tangent x. So what I know is that if I take the derivative of secant x, that is going to be secant x times tangent x. So here's another derivative formula that you will need to write down. Here are two other derivative formulas that I'll leave the proofs up to you. And you'll probably find them maybe in an exercise as well. In this case, the derivative of cotangent is equal to negative cosecant squared x. And the derivative of cosecant x is negative cosecant x cotangent x. Those probably are not too much of a surprise considering the relationship that we've seen in the past between how these derivatives, the cotangent and cosecant, and it's how it's similar to secant and tangent. So I would hope that these were not too surprising. So now we're going to move on and we'll take a look at higher order derivatives. The idea behind higher order derivatives is that these derivatives, the functions that we take when we take the derivative, those derivative functions are often smooth curves as well. And so they have derivatives that we could find and do further analysis on. So what we have with these, as we go through, we're going to notice that some notation that we have for higher order derivatives. We already know that if I'm using y, I know the derivative, the first derivative, is y prime. Or if I have it in function notation, f of x, I know we would use f prime of x. Or the other notation that we're familiar with is dy dx. That being the first derivative. Well, if I wanted to go to the second derivative with y would just be y double prime. Or f double prime of x. Or in terms of the notation, the Leibniz notation, it would be d squared y over dx squared. That is the second derivative of y with respect to x. If I go to the third derivative would be y triple prime or f triple prime of x or d cubed y over dx cubed as that third derivative. Okay. After that, we tend to, instead, we don't use the prime notation. So any further derivatives we just put the number in parentheses for these first two. So the fourth derivative would be y to the fourth, like this, in parentheses, or f to the fourth of x. That would be fourth derivative. Or if the Leibniz notation, the dy dx notation, that just continues on as is. So it'd be d to the fourth y over dx to the fourth. And I can do that for fifth, sixth, or even 10th derivatives if it's possible. One application for the idea of the higher order derivatives really gets into some physics with the position, velocity, and then the rate of change of velocity, which is called acceleration. I have a situation here where I have a position function where s of t is equal to negative 16t squared plus 120t plus 10. So the negative 16t, we're dealing in feet per second. We're dealing in feet and seconds in this case. So we have the negative 16 as our gravitational it deals with the help of the gravitational constant. The 120 is come out to be our initial velocity, and the 10 actually ends up being our initial position where we're starting out. And I know that the velocity function is just going to be the derivative. So if I take the derivative of s, I get s prime of t. That is equal to the velocity function, which we've talked about before. And that comes out to be negative 32t plus 120. And so what I know is that my velocity at any time t is going to be negative 32t plus 120. I can put in a value for t and I can come up with that velocity. But that velocity function is also a smooth, in this case it's a linear function, but it is a smooth curve, and so it does have a derivative. And what we have with that is that I would have s double prime of t, which would be the first derivative of the velocity function, and that is what we call the acceleration function, a of t. And in this case it comes out to be negative 32. Now in terms of units, our position function, the position function originally was in feet. Okay. Our velocity function would be in feet per second. And our acceleration function is going to be in feet per second or feet per second squared. So in this case, what we have is the negative 32 is the acceleration due to gravity in feet per second. So this concludes our video on product rule, quotient rule, and the idea of the higher order derivatives. We'll do some more work with that in class next time. I hope this has been helpful, and remember to complete your WISC, and we'll see you next class.